Part 2 of lesson 40 is jumping energy levels. And so we talked about a hydrogen atom. We previously said that in all the elements, they can have specific energy levels. So this is hydrogen right here. And these are the energy levels for hydrogen: 0.85, 1.5, 3.4, and 13.6. Electrons can only exist at these specific energy levels. What that means is, the reason they have negative is called the ionization energy. It means if you've got an electron sitting here in level 1 and a photon with 13.6 electron volts of energy hits that electron, it will ionize it. It will be enough energy to knock it out of the atom. If you had a photon that had, let's say, 15 electron volts of energy, then the 13.6 would ionize the electron, and then there would be 1.4 electron volts remaining for the electron to go do whatever, visit a friend, or go to 7-Eleven, who knows. Make sense? So what else does it say? It says if you have an electron at level 4, and let's say that electron drops down to level 2, then in that case, it will emit electromagnetic radiation, and you can find out what the energy or the frequency or the wavelength of that electromagnetic radiation is by using the energy levels. So if it goes from a 0.85 to 3.4, I'm just going to subtract those. 3.4 minus 0.85 gives me 2.55. Electron volts of energy. So if an electron is in level 4 and it falls down to level 2, it's losing energy. It emits that energy in the form of EMR, which will have that much energy. And then if I want to find out the wavelength, for example, I can just use this formula here. Therefore, lambda equals hc over E, and then I just plug those the numbers in. I'm going to use 4.14 times 10 to the negative 15 for Planck's constant, because we're in electron volts, times that by 3 times 10 to the 8th, divide it by 2.55, and I get 4.87 times 10 to the negative 7 meters, which happens to be 487 nanometers. In other words, that would be blue light, or something close to blue light, if an electron falls from level 4 to level 2. All right, and if an electron is in level 2 and absorbs 2.55 electron volts of energy, it will go up to level 4. All right. But what if an electron is in level 2 and absorbs, let's say, 1 electron volt of energy? So a photon comes along, has 1 electron volts of energy. What will happen? Will it go up to here, 2.4? No, it will not. It won't do anything. It won't have any effect on the electron whatsoever because of these discrete energy levels, this quantization. The electron can exist here or here, but it cannot exist in between. So if 1 electron volt of energy comes, it will have no effect on it at all. You will need 1.1. 1.1 electron volts of energy will be absorbed by this electron, and it will move up to this level right here. That's not right. 1.1. What am I talking about? That's not the right math at all. It's going to be 3.4. 1.9. 1.9. My apologies. 1.9. And I got that one wrong too. Oh no, I think that wrong. 2.4. So it has to have 1.9 electron volts of energy to make it up to this level here. Anything less than that, and it will do nothing. It'll just stay right here. Okay. So hopefully that gives you a little understanding of the energy levels and how they work. Now let's do the question. And the question says, determine the total possible energies emitted as electrons fall through these levels, So in other words, you could have an electron that starts at 4 and goes to 3, or starts at 4 and goes to 2, starts at 4 and goes to 1. Or you can have one that starts at 3 and goes to 2, starts at 3 and goes to 1, or this one here. So those are all the permutations of electron drops that you could have. 1, 2, 3, 4, 5, 6. You could have 6 different types of EMR emitted in the hydrogen atom with these 4 levels. Determine, B says, determine the wavelength of EMR emitted as the electron drops from 3 to 1. Okay, so we just did a very similar problem to that. Here's 3, here's 1. If it goes from 3 to 1, we're just going to subtract 13.6 minus 1.5, and that's going to give us 12.1. So in other words, EMR with an energy of 12.1 electron volts is going to be emitted, and then we can calculate the, what's it asking for? Determine the wavelength. Stick all that into your calculator, and you are going to get times 3E8 divided by 12.1, 1.2 times 10 to the negative 7. Right, 1.02 times 10 to the negative 7, which is 102 nanometers. Is that visible light? No. That has a shorter wavelength, therefore higher frequency. That is some form of ultraviolet light that's going to be emitted if an electron goes from level 3 to level 1. All right, and that brings us to the end of the Bohr model, onto the quantum model with the next lesson.